welcome everyone. Good morning, and thanks for being here in my talk. So today I'm going to present work. It's a joint work with Professor François Bacheli. It's about handover frequency in some dynamic communication network. And okay, so the outline of my talk is to, let's say, um, use some satellite constellation at the beginning and define what do we mean by handover there. And let's say later I'll take some toy examples to motivate. Sorry. Okay. So later I'll take some toy examples just to keep the essence of the problem, but still we can extract a lot of insight that is already present in the higher model that is with the constellation of satellites and in two-dimensional, three-dimensional model. So there I will determine, let's say, the handover frequency or gap between two consecutive handovers. Let me define what do we mean by handover. But first, to start with, what do we mean by a satellite constellation, or to be specific, a LEO satellite constellation is that we have orbits, and you can, let's say, define the orbits as a Poisson point process, and on each orbit, these are like line Poisson line process on the sphere, and on each orbit you have Poisson point process, and this way you can generate the location at a particular instant, the location of the satellites, and the satellites are moving in their own orbit without leaving them, even without changing their altitude. And what do we mean by handover there is, let's say one user is sitting somewhere and it is served by some satellite that is the closest one. And as all the satellites are moving, so some other satellite will come even closer at a later instant. So whenever this change of nearest satellite happens, we call this change as handover, and the time at which it happens, we call it handover time or handover epoch. So what happens in the satellite constellation is that all these satellites have their own coverage areas, and if the satellite is moving in its orbit, it carries its own coverage area that is projected on the surface of the Earth. Okay, so if you consider some user in, let's say, one of the balls, then or the coverage area of a particular satellite, but after some time that coverage area will move away and some other coverage area will take its space, right? So that's the time when this handover happens. So formally, let's say we start with a toy model on two-dimensional plane. We take, let's say, a Poisson point process. That's the initial location of base station, or we call it station, let's say, to be keep the problem more abstract. And each of these base stations or stations have their own service region that you can define as a Voronoi tessellation on the plane, right? And now you can give mobility to these base stations. So what you say is, to start with, you give a random direction uniformly chosen to all these base stations, and they are not changing their direction over time, and they are independent among each other. Okay. So the serving base station is the nearest one to the user. And whenever the serving base station changes, you will see that a handover is happened there. Okay. So maybe I'll run a small simulation, animation about this. So, okay. Oops. It's not even number. Okay, let me load some random number of points. Uh, let's say 100. And you have the stationation that are colored for different base stations, right? So now I want to give mobility to these base stations. So what you do is, let's say I'll give them some speed, and direction is uniformly chosen randomly. So if you start the motion, you will see, and let's say where my cursor is there, there is one user, and you can see this time a new satellite or the base station that comes in as a serving base station, right? So these are the times when this boundary are crossing the user or sweeping over the user is called as handover, epoch or handover. So yeah, so let me go back to my slides. Okay, so you can really plot all the time points whenever these handovers are happening, and it's a point process on the let's say time axis, but you never know where you are starting your observation, so you can plot these points on the uh, real axis, right? So my goal is to determine what is the frequency of handover. That means in a unit time, how many times you are performing the handover, right? And the later question will be, let's say, the gap between two handovers. That means if we go back to the animation, how much time you are spending in each of the cell. So why it is important? Because during the time you are connected to one base station, you in the base station will, I mean, you can determine the total amount of data you can download using the time, the gap between two handovers. Using that, you can determine how much data you can download being connected to a base station, right? So this is why we need to know the distribution between distribution of the time gap between two handovers, right? So okay, so if you go even simpler, let's say the base stations are not moving, but the user is moving along a straight line, right? So it will keep crossing these boundaries of the coverage regions of each base station. So you can determine in the handover frequency there as well. Okay. So this is the first result in the previous simpler setting where you can determine the handover frequency in terms of the speed of the user and the intensity of the base stations, right? But let me put you this question. Okay, it's already on the slide, but do you think the handover frequency will be the same both in static and dynamic case? I mean, we see there are, I mean, because of the motion of the satellites, you may think intuitively that you may see more handovers or probably less. But actually, we proved that this turns out to be the same. So, I mean, the only thing that needs to be preserved is the direction. I mean, without changing, the base stations are not changing the direction. But if you consider more complex setup where the base stations are changing direction, that will be more complex. So I will not go into that in this setting. Okay, so just to say a few words why we need this, because in the, I mean, along the motion of the satellites, there are a few things that tells you about the signal you receive from the base station and the interference you receive from all other base stations. So you need to know for each time instance, what is the distance, if you consider the attenuation function as a function of the distance, right? So if you want to compute the received signal power, you need to know the distance between the user and the serving base station, right? So at a typical time, the distance usually follows Rayleigh distribution. But let me put you another question, that what happens during handover time? Because at handover time, you will see two base stations that are equally distance apart, and all others are distributed, let's say, as Poisson. Okay, but will it be still Rayleigh? And maybe we'll answer that later. But these distances are important to compute, let's say, SINR, SIR, SNR, and the Shannon rate in the system at each typical time, even at handover times, right? Okay, so here I'm defining the, let's say you start your system at a handover time. That is important, right? Then you can compute the gap between two handovers as when you see the next handover, if you start at a handover time, right? So T1 is the random variable for which defines the handover time, okay? So some questions that are that we are answering here is, let's say, what is the distribution of the handover time, and what is the distribution of the rest of the points um, at handover epoch. Let's say you just performed a handover. That means you have two base stations that are equally distance apart from the user, and all others you don't know about them, but we can show that they are also Poisson distributed. But usually in Poisson point process, if there are 2 points that cannot be equally distance from the user, right? So okay, and we determine what is the distribution of the handover time under the palm. Palm means you are just performed the handover. Okay, so here are these answers that, let's say you just performed a handover. That means you have two base stations equally distance apart from the user. So this random variable has a Nakagami distribution, and the parameter of the distribution, it depends on the parameter of your initial system, that is the intensity of the point process. Okay, and we can prove that the points in the rest of the region that is outside this ball of radius, this handover distance, they also follow Poisson distribution. Okay, so in the simpler setting where the base stations are not moving, that is the static case. This result has been done before in many other situations. And this is like the linear chord length distribution or in a Voronoi tessellation, or you can start with any stationary point process. Okay. So to go to in a much more complex setup where you can consider there are two type of base stations moving at two different speeds. Okay, they are constant. Why it is important? Because in the LEO and MEO satellite constellation, because of the altitude, different altitude of the satellites, they have different speed. So within the same altitude, all satellites preserve their speed, but within different altitude, they are at different speeds. So in our time model, uh, we have derived the handover frequency in the two-speed setting. Even let's say if you start with the n different type of speed, there are n species, let's say, then you have this composite formula for or composite expression for the handover frequency that depends on the total intensity of points, the speeds, individual speeds, and the proportion of the points for two different species or two different type of base stations. And there is a cross product term also present in the handover frequency. Okay, so this and this generalizes to let's say if you start with n different type of base stations, so and then you have similar expression for the handover frequency. Okay. And just to, I mean, I gave a lot of motivations before, but The next line of work will be to understand these problems, let's say on 2D, with the base stations are moving on some random environment that is, let's say, you can consider as Poisson line process or Manhattan line process, and also single and multiple speed in the random environment. Okay, and this LEO and MEO satellites are motivates also this type of model, because these orbits are also Poisson line process or Poisson orbit process, right? So, and one can also consider, let's say, mimicking the spherical scenario where a user has a visibility area. That means it can see not all satellites. It can see only a few satellites that are only within the horizon, right? So it does not go beyond that. So one can consider this toy model in a finite visibility case as well. So I mean, but in real system, the user may not be served by the directly by the satellite. The signal can come from hopping from one satellite to the other and to the user, right? So that way you need to understand what happens if you have routing in your algorithm of sending the signal, right? So that will be final goal of this. Thank you. Sorry for the delay.
Thanks. I might reveal my ignorance here, but if I have a satellite moving, the angular speed is constant. What you're looking at in your model is the linear projection down to a plane on the surface, right?
Yes.
So if I have an angular movement in orbit, is that still a constant angular speed? Is that still a constant speed on the projection? Doesn't that change?
I mean, it does not change for the if it is moving in a orbit, but for different satellite in different orbit,
of course, yeah,
it will be different. Yes. Yeah.
Okay.
Thanks for the talk. It actually brought me back many decades back. I did my dissertation on cellular system, and it was called handoff instead of handover at that time.
Yes, that's the same name.
One question that is that so when you hand over, it means that, or hand off, there is some capacity on the other device that you're moving to, but that's not always the case, right? So, you know, if you could have a satellite that's already full because it's serving a bunch of users.
Yes.
And so and you've looked at the SINR, right? So you know the distribution of how the signal to noise ratio. I guess, could you characterize in some sense how much time I have, right? So you could decide to do the handover before or even delay it depending on the availability of capacity on, you know, whether the satellite you're on or the one that you're trying to hand over to.
Yes, this is a completely different, I mean, you say another layer of, complexity of the problem, because you need to manage your, how many times you can perform the handover, right? So in a different project I was working on in the two-dimensional case where the base stations are fixed, but the user is moving, then you can perform a Markov decision process to decide whether depending on how much data you can store and capacity and all, you can decide whether to perform the next handover or not. So I'm sure maybe in the satellite setting that this work needs to be done. So.
So I'm just wondering if anyone has collected data from these satellites to show that the Poisson modeling, does that actually reflect collected data somewhere, or is that just?
You mean the locations of the satellites?
Yeah.
I think so. I mean, we have this collaboration with this company Constellation Technologies. So we are collaborating with them, working with the data collected by them. So,
I see.
but
The Poisson assumption is not
it
just
is,
a convenient modeling tool, but actually reflects what really happens. or
yes, I mean, one
approximate.
can really approximate, it may not be a good approximation, but one can approximate these locations of the satellites as Poisson point process.
I see.
Maybe the Cox point process, not Poisson point.
No, yeah, that's what I meant, yeah. So that's fine, you know, it reminds me, and François knows this very well, but you
Yes.
know, well, in internet traffic modeling for decades, people used Poisson processes to model a lot of things about that. And then Walter Williger and all of his colleagues show that it's actually not true in backbone networks, right? That are traffic traveling over fibers and Ethernet and stuff like that. So, but it took quite a lot of data and work to figure that out. But and decades after people had been using Poisson models. So I'm just wondering here, but if you have data from satellites, then that's great. Yeah.
I mean, this is a very beginning part of this line of research. So, I mean, we can gradually put one layer of complexity every time, and then try to see whether it matches with the real system. So, yeah.
Thank you. Very interesting. Talking about layers of complexity, would it be possible to assume that some of these satellites have processing capacity, something like edge computing, and consider the possibility of moving your computations to this subset, to one of these subset of satellites that allow you to implement some computation?
To be honest, maybe, I mean, like, I may not be able to answer this because, I mean, I'm more working in the theoretical side of it. So probably some expert with the edge computing and things like that can answer.
No, but that just means studying how you would route your computations over this subset of satellites that have computing capabilities.
Perhaps I can say a word on that because actually it should be good for our Bellax colleague, but the Chinese have made the first key distribution from a satellite. It was 2 or 3 weeks ago. So there is services. Actually, currently for the next 20 years or 10 years, there will be no edge computing on board because, I mean, there is a problem of energy expenditure. You have to, I mean, you can't do heavy computation on board of satellites currently, I mean, for the low orbit because they are very small, and so having heavy computation is not really that's more futuristic. But there is a key problem of energy expenditure in the current LEO deployments. Nevertheless, I mean, there are first experiments along this line, and this Chinese first for a couple of weeks ago is quantum key distribution, exactly along the lines of what was described the other day.
I think there were several years ago already by Chinese an experiment on quantum key distribution, but I was not aware of this. So I am interested for the pointers issue.
So can you go with a more queuing approach once you know the timestamps? So it is more resembling a queue, right? So it's like your user is waiting for which satellite is going to arrive at random time instants, and then that might be useful to compute a distribution of it's like a waiting time distribution.
Yeah, that can be a good approach. That can be.
Yeah. So because if you know the distribution